recently the NACL 2019 Best Resource Paper Award. He's currently an ERC grantee. And yeah, Jonathan, welcome here, and we are very much looking forward to your talk.
Thanks for the invite. Oh, okay, now I can share my screen. Okay, can you see my screen?
Yes.
Okay, so hi, I'll talk a little bit about compositional generalization. Thanks for the invite. It's an honor to be with everyone. So the field of natural language processing has been going through a crisis of evaluation recently. And you can summarize this crisis by the fact that when you measure the performance of NLP models on standard benchmarks, many times you see that they have superhuman performance. But when you actually play around with them and look at what they can do, you find out that maybe the performance is not as good as you would expect. So to kind of like reconcile or combat this problem, this discrepancy between the numbers that we see and the feeling that we have inside, one of the main things that people have been doing is starting to evaluate the generalization, the out-of-distribution generalization. So at test time, you sample examples from a different distribution than the one that you saw at training time. And it should be some distribution that humans are good at generalizing to, but we should see whether our models do well or not. So there are many possibilities. One is cross-domain generalization, or domain adaptation, where maybe you see news at training time and reviews at test time. Or maybe it can be temporal generalization. This is recently from DeepMind, where you see one period of time in training time and another period at test time. And there's a lot of work on adversarial examples, where small changes in the input should or should not flip the label. And this can be done automatically or with humans in the loop, and so on. But today I want to focus on one specific type of out-of-distribution generalization, which is compositional generalization. And this is about the fact that we as humans, if we know what a winged insect is, and we know what a giraffe is, if someone tells us what does a winged giraffe looks like, well, you know, it will be something like this maybe. And the reason this is kind of like a nice setup to explore is because, first of all, you can operationalize it. You can actually build data sets where the output is some structure, and you can kind of like try to make sure that all of the parts appear in the training set, but the things that you actually see at test time are new compositions that you have never seen before. And secondly, this is something that humans can do quite well. So we know that humans can kind of like interpret new words and new compositions all the time. And this is what allows us to describe things like a cat stuffed in a box, or a pet peeking from a watermelon. And even though you've never heard this, this is like this productive nature of natural language that allows us to communicate infinitely. So this has led to quite a lot of interest in this field of compositional generalization. And the general conclusion from recent years is that our standard architectures fail at compositional generalization. When I say standard architectures, this is more or less synonymous with transformers nowadays. I don't know if that's a good or a bad thing, but this has been shown in visual question answering and in semantic parsing, and you get a lot of papers that show that while people compositionally generalize, when you measure this in some task, you see that actually our models currently do not generalize well. So what should we do to try to address this mismatch? Well, there are two possible approaches. The first is to fix the model and just change the data. So if we expose our models to enough data that shows how different compositions result in different labels, then maybe eventually the solution that our model learns from the training data will be the one that compositionally generalizes. But this might require a lot of data. There's some evidence for that. And you know, this explodes combinatorically with a number of compositions. A second approach might be to go back to the models that many of us knew and loved 5, 6, 7 years ago that were very compositional in nature. So basically, the model constructed and composed things quite explicitly. And what we want to ask is whether we can improve compositional generalization by taking the good parts from the neural models that we have now and combining them with like a strong compositional inductive bias. And the short answer is yes. So we show this in two different works. So one in visual question answering on the left here, where we show that so yellow is us in general, so that our model is a lot better than previous work in terms of compositional generalization on these synthetic visual question answering tasks. And also in semantic parsing, which is mapping from natural language utterances to these logical forms or programs, we get substantial improvements by having these tree-based inductive biases. So let's dive right in. So this is work with collaborators from Tel Aviv and the Allen Institute. And the setup is visual question answering, where we get this question that is kind of like compositional. It requires multiple reasoning steps. What is the shape of the, etc. And at training time, we only see the answer, cylinder. So no one is telling us that there is some recursive compositional structure here. We're just given the answer, and we need given a question and an image to find the answer. So this is the setup. And our goal is to show that by having an explicit inductive bias for compositionality, we will get better compositional generalization. So this is a pretty short talk. I'm not going to talk about the details of the model a lot, but it's kind of like a continuous relaxation of CKY, where you recursively start from words, move on to phrases, and then compute something for the entire utterance, where for every span, you compute a representation. This is a vector, and a denotation, which is a distribution over the objects in the image. And for example, if you want to compute this for the phrase tiny shiny sphere, well, there are two possibilities. Either you compose tiny with shiny sphere, or you compose tiny shiny with sphere. So you have some differentiable function that will compute that for both cases. And in the end, the final representation denotation will be some weighted average in order to make this entire process end-to-end differentiable, so we can use the magic of backpropagation and learn good representations. So this is more or less how it works from words until you have it for the entire utterance. So what would that look like quickly? So for the word sphere, we might want the denotation to be these spherical objects in the image, and then green will be the green stuff, and then hopefully green sphere will result the function that will compute the intersection, and so on until we will have some denotation, which is some object in the image from which we will extract the answer, which is cylinder. So this is roughly the model. It's written in short in here, computer representation denotations for spans of length 1, length 2, etc. And then you take the final denotation and representation for the entire sentence, and with a feed-forward network, extract the answer. That's it. And one nice part about this is you don't only get the answer, you also get you can decode an approximation for the argmax tree, the most probable tree, which gives some interpretability, but of course it's a distribution. So let's see how this works. And just as a sanity check, we can evaluate this on a completely compositional task, which is evaluating arithmetic expressions. And the compositional split basically designs that there are some positions in the input where only certain operators appear, and then at test time, different operators appear in those positions. And we can see that in a random split, a transformer does very well, and our model does very well as well. But once you move to the compositional split, the transformer performance is very low, and ours remains quite high. Then if we look at actual visual question answering, which is CLEVR, which is a bunch of synthetic questions over synthetic images, and closure, which is a compositional split where you get new compositions at test time, well, we see a pretty similar phenomenon where for the random split, our model does quite well as previous works. But in the compositional split, you get dramatic gains in performance. And just because of lack of time, I think I'll skip the CLEVR-Humans part. And again, it's important to notice that our model does not only provide an answer, it also provides a tree. And we have some user case studies showing that this is actually useful for people that are trying to understand what the model is doing. A second paper that we had on this with Jonathan Herzig, I think he's here, is doing something similar for semantic parsing. And semantic parsing is the task of mapping from natural language questions to logical forms or programs. And here again, the standard approach is to use sequence-to-sequence models, end-to-end differentiable models. And in these models, there is no alignment, specific alignment between parts of the input and parts of the output. So no one tells you that the word capitals corresponds to the predicate capital and that the word borders corresponds to the predicate next to, except for some soft attention. And the question is whether by using a strong compositional inductive bias, this will lead to better compositional generalization. And in this case, we think that because we have these logical forms, which are a strong supervision, we can have even a simpler model with a strong compositional inductive bias. And we use what's called span-based semantic parsing. So again, just one slide, because this is a short talk. What do we do here? Well, we basically train a span prediction model. What does this span prediction model does? Well, for every span in the input, for example, the word capital, it will have a distribution over a fixed set of categories. So the word capital will hopefully put all of the probability on the predicate capital. And for the span New York borders, hopefully we will predict that it should be a node in the output tree. This is what this join means. But for the span what is the output, it should not be a node in the tree. And after we have this set of probabilities, just like for every span we have a distribution, we can use CKY to predict the best tree. And from this tree, we can decode the final logical form. So I claim—
Jonathan, maybe your slides, I think, froze. I don't know what's going on, but we still see the diagram.
Which diagram? What do you mean by diagram?
Evaluation, CLEVR and closure, where you have different colors, blue, green, yellow.
So it's been a while. Should I stop share and try again?
Yes.
Sorry. Let's see. What do you guys see? Like is it moving now?
It has started sharing, but we can't see anything yet. So it seems there's a problem.
Okay, let me try again. Do you see anything now?
No, same thing. So it starts sharing, but then no image is appearing.
Okay, let me try sharing the entire computer. Let's see what happens. Desktop 1. Nothing?
So same story.
I can try to disconnect and
maybe restart Zoom. Sometimes it happened once to me.
This is never. Okay, so I'm gonna be back soon.
Let's hope for the best. I guess he's joining again.
Yeah.
Welcome back.
Yeah, but now it says host disabled participant screen sharing.
Oh, maybe this is the reason.
No, I enabled you again. When you log out, you stop being co-host. So now you're enabled again.
Okay. Do you see anything now?
Yes.
Do you...
Semantic parsing.
Okay. Should I start from? Let's just move on to the semantic parsing part. You tell me how much time should I speak from now?
Yeah, I guess like 4 minutes. Is that fine?
Yeah, we'll do with 4 minutes. So I talked about how this compositional inductive bias works for visual question answering, and now moving on to semantic parsing. And in semantic parsing, the task is to map from a natural language question to a logical form, to a program that is executed on a knowledge base. And again, there's the same issue. The common models are end-to-end differentiable models, where the only thing that ties the output to the input is soft attention. But nothing explicitly says that the word capitals corresponds to the predicate capital and that the word borders corresponds to the predicate next to here. Do you guys still see things moving, by the way? Okay, great. So here, though, we have much stronger supervision. We have not only the answer, but the logical form. So we decided to try an even simpler model with a strong inductive bias. So what is this model? It's what's called span-based parsing. And in span-based parsing, you map every span to a finite set of labels. For example, the word capital should be mapped to the predicate capital, which is from the knowledge base. There's a fixed set of predicates. And the span New York borders should map to join. Join means this should be a node in the output tree, but the phrase, the span, what is the, should not be mapped to any node. And once we have this set of distributions over a quadratic number of input spans, you can use CKY to find the most probable tree approximately, never mind the details, and compute the final logical form. And the point is that we're quite good now at NLP in span prediction. There are very good models for span prediction. So all the parameters are in span prediction, and it's very, very simple. It's worth noticing that we don't really have supervision, which is trees. So we have to take a hard EM approach. But again, because I'm out of time, I'm just going to skip that. So you can trust me. This needs to bootstrap somehow, and we do that. OK. So we evaluate this also on multiple data sets, and I'll just show one result. So on Geo880, which is like a classical semantic parsing data sets with like questions on US geography, again, sequence-to-sequence models with Elmo and BERT and grammar-based decoding all do not do very well. But once you use this inductive bias, you get much, much better performance. OK, so I guess what's my point? It's not that my point in life is for everyone to work on tree-based models. It's not my mission in life at all. But it's worth noticing that in early 2016, I was happily working on these tree-based models. And then 6 months later, it was gone, basically gone. And of course it was. I think it's very, very understandable. And the reason is because these models are so simple, so general, efficient, and flexible. They just resolved so many of the pain points that we had. So there were these issues where a single word mapped to like a complex logical form. This is a non-issue in sequence-to-sequence model. There were these issues that a single word in the input mapped to multiple things in the output, or that it just mapped to nothing in the input. It's not an issue in a sequence-to-sequence model. What about non-projective trees? You have extensions to CKY. Well, this is not an issue in sequence-to-sequence models. But it's worth noticing that we did lose something. Something was lost. And one thing that was lost is this kind of like inherent ability to generalize to new compositions. So I guess what I want to ask is what's in the middle? Are there things that we can think about that are kind of like in the middle and join the good of both worlds? So I think there's a lot of interesting open questions in this field right now. So for example, how do we handle the fact that language is not really fully compositional? Red wine is not red, white wine is not white. So we need to do something about that. How do we kind of like inject these compositional biases into transformers, which we all know and love? They kind of work. So can we just do it there? Can we pre-train our models to just exhibit compositionality out of the box? Can we solve this by fixing the model and just doing some smart data sampling or something like that? How can we generalize to real images? I guess there's some typo here. So I think there's this experiment that we did on this pretty compositional architecture kind of like raises a lot of interesting follow-up questions that I hope many people will explore. So sorry for the technical difficulties, and I just want to thank my collaborators. That's it, I'm done.
Yeah, thanks a lot, Jonathan. Perfect timing. We are a bit behind the schedule, but I propose that we have a couple of questions. Now, are there any questions? I don't have any in chat right now.
Hello, may I ask a question?
Sure, please.
I thanks, Jonathan, for the great talk. So I had a question about the first part of the talk, about the visual reasoning part of the talk. And so I remember one slide in which the transformer was shown to be to achieve a very low accuracy on the compositional task. Yeah, around 2.9 or 3%. And I was just wondering what is chance level in that task, if it's well, yeah, if the transformer is basically getting an accuracy that is on par with just.
I think random was 1%. I think it was like even distribution over integers from 1 to 100, but you can check the paper. I don't remember exactly. It was a bit better than random. In some other compositional splits, the transformer was like 30. So you can think of many splits. This is one where it specifically sucked, but there are others where it does definitely better than chance.
Okay, thank you.
Thank you. Is there any other question?
James Henderson.
James has a
Yeah, I have a
question.
question. When you talk about compositionality, it kind of seems to presuppose this hierarchical structure, the kinds of structures you were talking about. So in syntax, there's two perspectives on how the syntactic structure can be represented. One is this kind of hierarchical nested structure, and the other is dependency structure. So it's basically a graph of where the nodes are words. I think that the second kind of graph-based structures fit a lot better in Transformer than the hierarchical structures.
Yeah,
and I wonder your thoughts on how to get this kind of semantic compositionality into a graph-based perspective on the structure of language.
Are you, I mean, I kind of like get the intuition that dependency parsing is better suited for transformers because it's like pairs of words, right? Everything is related to pairs of words, and there's attention.
Right,
but
attention is the relation between the words, exactly.
So, I mean, I can imagine that you can like constrain the attention structure in the transformer layers to kind of like be similar to dependency trees, like Emma did in her best paper.
That kind of thing, yeah. But then how would you have the kind of compositional semantics in that kind of graph representation?
I mean, for us, I mean, we're not building on transformers. So like a transformer is like a block that like takes a bunch of vectors and outputs like some other vectors. So you can like have every, like the head take a bunch of modifiers and create a new representation. I mean, I think there's definitely generalizations that can accomplish that are pretty natural, and it might work just as well. I don't have like a strong preference between the two formalisms. I guess it seemed more natural for us to use like constituency trees in this case. But there are,
all right.
Yeah, okay, maybe I should stop. We can take it off.
Yeah, thank you very much. So now we have 10 minutes for a break.